Welcome to ECE 761 Robotics, lecture number 9, LaGrangian Dynamics. Now the next couple of lectures we'll be looking at the dynamics, trying to control the dynamics of a robot manipulator. Robots are inherently nonlinear with all the sines and cosines and gravity terms involved. So we need a way to find dynamics for nonlinear systems. LaGrangian Dynamics is such a tool. It can handle nonlinearities. The idea is to define the energy states in the system. Once I specify the energy in the system, specify how the energy changes. If you know how the energy moves throughout the system, you basically know the dynamics. A couple definitions to start with. Ke is kinetic energy in the system. Pe is the potential energy. A del is a partial derivative. A d is a full derivative. And the Lagrangian is kinetic energy minus potential energy. Start out a little bit on partial derivatives and full derivatives. A full derivative contains partial derivatives. For example, think about it like you have a hill. Here's the top of a hill, I'm moving along. I want to know how fast am I ascending. To do that, I can use partial derivatives. What's the slope in the x direction times how fast I'm moving in the x direction, plus what's the slope in the y direction times how fast I'm moving in the y direction. Put those together, I get how fast I'm ascending. Now when you do that, I don't want to double count. The fact that the slope changes in the y direction, I don't really care when I take the partial in the x direction. That's in another term. So anything that's not the term that you're taking partial of is a constant. And you kind of think of it this way. The x's sort of cancel, so I have dh dt. The y's sort of cancel, dy dh dt. So it sort of works out. Let's go through an example. Suppose I have a is x y squared t, b is 3x cosine t, and I want to find out what is the full derivative with respect to time of ab squared t cubed. Now to do that, I will have three terms. What's the partial with respect to a times how fast a is changing, plus the partial with respect to b times how fast b is changing, plus the partial with respect to c, or t, times how fast t is changing. When I take the partial with respect to a, I don't care that b and t are also changing. I just say anything that's not a is a constant. So the partial with respect to a is just b squared t cubed times the partial of a with respect to t, which is up here, just xy squared. Second term, partial with respect to b is going to give you 2ab t cubed times the partial of b with respect to t, which is there it is, minus 3x sine t. Plus the partial with respect to t gives you 2ab t squared, and the partial of 2 with respect to t is just 1. So this is the full derivative of that. Notice the partial derivatives are part of a full derivative. We'll be using that. The procedure for Lagrangian dynamics is as follows. First, define the kinetic energy and potential energy in the system. Form the Lagrangian, then take the full derivative with respect to t of the partial derivative with respect to xi dot minus the partial derivative with respect to x. If F is a position, F is going to be a force. If x is an angle, F is a torque. And let's go through an example. Suppose we want to find out the dynamics of a rocket. The potential energy is just mgx, where x is the direction it's flying going straight up. Kinetic energy is 1 f mv squared, 1 f mx dot squared. Now set up the Lagrangian. Kinetic energy minus potential energy. Now take the partials. The force is the full derivative with respect to t of the partial of L with respect to x dot, minus the partial of L with respect to x. Taking the partial of L with respect to x dot, there's an x dot right here, gives you mx dot. There's no x dots over here. I don't really care that x is related to x dot through an integral. Anything that's not an x dot is a constant. Now take the partial with respect to x. Again, there's no x's over here. X dot is different than x. So that's 0, minus mg. Now take the full derivative. The full derivative would be m times acceleration. There's the second term, plus m dot times x dot. If the mass is changing, I get this term, plus mg. This term doesn't show up in other forms of dynamics. It does show up in Lagrangians, and it is real. If the rocket is burning fuel and losing mass, this does affect the acceleration. Now let's take a second example. Let's look at the dynamics of a ball rolling in a parabolic bowl. To find that, I first define the kinetic energy and potential energy. Potential energy is just mgy. Y is 1/2 x squared, and I'm going to put everything in terms of x. Kinetic energy is 1/2 mv squared, plus as the ball rolls, I have rotational inertia, plus 1/2 j theta dot squared. For a ball, x equals r times theta. Take the derivative, x dot is r theta dot, so I can substitute and get an x dot in here. Velocity is x squared plus, or x dot squared plus y dot squared. Y is from here, take the derivative, plug it in, and eventually get this term. J depends upon what type of ball it is. If it's a point mass, the inertia is 0. Hollow cylinder, it's mr squared. I'm going to assume a solid sphere, like a ball bearing or a marble. There, the rotational inertia is 2/5 mr squared. So substituting, the r squareds cancel, and I wind up with kinetic energy is 0.7 m times 1 plus x squared, x dot squared. Now we'll form the Lagrangian. Lagrangian is kinetic energy minus potential energy. Step 3, take the partials. It's the full derivative of the partial vel with respect to x dot minus the partial vel with respect to x. Partial with respect to x dot is right here. Gives you 2 times 0.7 times m, this term. Partial with respect to x, here's an x, gives you 2x times x dot minus mgx. Now take the full derivative. The full derivative, assuming mass is constant, will be the partial with respect to x times the partial of x with respect to t, plus the partial with respect to x dot, partial of x dot with respect to t, and this term. Partial with respect to x is, there's the x, gives you 2.8 m x dot times the partial of x with respect to t is x dot. Partial with respect to x dot, here's the x dot, gives you these terms, times the partial of x dot with respect to t is acceleration, and the last term. Simplifying gives you 1.m for mx x dot squared plus here. If the force is 0, meaning you're in free fall, here's the acceleration. With that, I can simulate a ball rolling in a parabolic bowl. Basically, I specify position, velocity, calculate acceleration, integrate acceleration to get velocity, integrate velocity to get position. If I know x, I know y, and plot it. And this is what it looks like. This is the ball rolling in the parabolic bowl, and it's kind of slow. It really slows down when I'm recording. The ball accelerates as I get to the bottom, and then comes back up. So the other parts of the code, that little line through it is really just decoration. That helps you see that the ball is rolling and how fast it's rolling. This will be the max velocity, then it slows down as I go left. This is a fairly complicated system. The beauty of the Lagrangian dynamics is it's fairly complicated, but you can still find the dynamics using Lagrangians. We'll be using Lagrangians a little bit later to find the dynamics of robotic manipulators. The homework for this week is, for a similar problem, a ball rolling in a bowl of a different shape. Find the kinetic energy, potential energy of the ball, and in the bowl for the homework problem. Form the Lagrangian, take the full derivatives and partial derivatives, and from that find the acceleration versus position. And kind of optional, but it's kind of fun. Let's modify the bowl program to show the ball rolling in the bowl of the prescribed shape. So that's lecture number 9 for ECE 761, Robotics.